All right, welcome everyone. So last time we saw the 7805 regulator or the 78XX series, right? Everyone can hear me, right?
Yeah.
Perfect. Thank you. Okay, so last time we saw the 78XX series, and for example, a 7805 gives us a constant voltage out as long as we just follow a couple of things. And the only thing that we really needed to pay attention to was, first off, we attached some filter caps. And we talked about the purpose behind these caps last time. I said that the input cap was mainly for dealing with kind of parasitic inductance in the lines. And that helps us to be able to achieve a more steady voltage. And then on the output, we had this other cap, and its main goal was to filter out some ripple that's created from the internal circuitry. And we haven't seen the inside, so we will see the inside in a minute. I'll have to kind of look at it a little bit from an overview because we don't know all of the components that are actually used inside for the construction. But nevertheless, this is our fixed voltage regulators. Okay, so when you purchase these, they come preset for a specific voltage output. And then there were two things, the filter caps that we need, and we need to pay attention to that dropout voltage. You want to stay 2.5 volts above your output. So VN in this case needs to be 7.5 or greater. Okay, now we also have, as well as fixed voltage regulators, we have adjustable voltage regulators. And the adjustable voltage regulators, we're going to go with the kind of the most common part that we have that's been with us for quite a while. This is the LM317. Now, the LM317, if we look at, well, the schematic symbol, we're going to have 3 pins. So very similar to our fixed voltage regulator. And in fact, the internal circuitry is very similar to that of a fixed voltage regulator, but this is going to give us the ability to change whatever the output voltage is. So we have 3 connections. Ooh, that should be V out. Sorry, this should be V out. We have a V in. Now we are still going to need these filter caps. Now the filter caps do change a little bit. This is what's recommended by the manufacturer of this device, to put a zero 0.1 microfarad on the input, and on the output to have a 1 microfarad. Okay, so that is similar but swapped from the 7800 series. So with the 7800s, we would like to see, or at least as the manufacturer recommends, 1 microfarad on the input, 0.1 microfarad on the output, whereas on the adjustables, generally speaking, zero 0.1 mic on the input and 1 microfarad on the output. And then notice, instead of having a ground connection as we did, we actually have this pin that's labeled as adjust, and this pin is what's used in order to set the voltage at whatever we want. Now, the way you set the voltage output for the LM317 is with these two resistors, R1 and R2. Now, R1 and R2, if you think about what's going on here, we're actually taking whatever V out is, and we've set up this voltage divider. Well, these resistors are considered to be feedback resistors because the LM317 uses the midpoint between these two resistors. In other words, uses the output from this voltage divider that's created between R1 and R2 in order to sense the voltage out over here. Okay, so we're taking this voltage out and we're dividing it to a lower voltage, and then the LM317 uses that as a reference to adjust V out. And then as V out changes, again, this voltage divider looks at the voltage over here, divides it down, and then the LM317 looks at this divided voltage again and adjusts accordingly. It constantly does this. So whenever we have this kind of a loop where you're looking at the output somehow and then adjusting and then looking at the output and back and forth, and you'll see this when I draw the internal circuitry, it's a bit more clear. But this is referred to as feedback. So let me label these as our feedback resistors. Now, as far as using this device, it's very easy because we just have a formula that we can plug into to determine what the output voltage is for a given set of feedback resistors, or set the feedback resistors for a desired V out. And so the equation that's used is going to be V out is equal to Vref times 1 plus R2 divided by R1. Okay, and now V out makes sense. That's our desired voltage output. R2 and R1 makes sense. Those are our feedback resistors. We need to choose two resistors in order to set the output voltage. But Vref, what is Vref? Vref is internally generated by the LM317, and it's actually going to always be at a fixed 1.25 volts. Okay, so Vref is always going to be 1.25. So you can think of the equation as just being V out equals 1.25 times 1 plus the ratio of R2 to R1, R2 divided by R1. And that's what sets out our voltage. Now, we do have some rules when picking R1 and R2. So let's go ahead and just call these rules of thumb. Pick R1 to be equal to 240 ohms. Okay, so pick R1 to be equal to 240 ohms. And definitely keep R1 between 100 ohms and 1K. Now, there is a specific reason for this, but it is a little I want to say a little above and outside the scope of this class for the reason to stay within 101K. The manufacturer tells us that we should do this, and that's generally good enough for me when you're working with a component, when you look up the data sheet for it and it gives guidelines. But the reason for doing this is, as I mentioned, there's this feedback loop that's over here. Now, feedback loops have the ability to oscillate if things don't change fast enough. And so if you're looking at the voltage here and then this device, the LM317, needs to compensate for that by increasing and decreasing the current, then this resistor over here can cause issues where things move too fast or not fast enough. And so these are the range of voltages, range of resistances that you want to stay in order to maintain what they would refer to as loop stability, because we have this feedback loop over here. Okay, so let's go ahead and let's just design a 5-volt regulator using this adjustable. So let's say we're going to make a 5-volt regulator from an LM317. Okay, so we know we have that equation that we need to plug into, and we have some recommendations for picking R1. So let's go ahead, fill out that equation. Our V out, we want it to be 5 volts. That's our desired output from here. We want to create a 5-volt regulator. And then our reference voltage is 1.25 volts times 1 plus R2 divided by R1. But as we said, we need to pick R1, and we should pick it to be 240 ohms unless there's a better reason to deviate from that. So let's do R2 divided by 240. And now we just solve for what R2 is. R2, therefore, is going to be equal to 720 ohms. Okay, so we have R1, which will be 240. We have R2, which will be 720. And we go ahead and just plug that into our circuit. Make sure we have filter caps. It'll be 0.1 on the input and one micro on the output. For R1, 240, and for R2, 720. Okay, so this is actually a really easy device that does quite a bit for us. Now, this is 5 volts, so I will just go ahead and draw this with a top hat to signify 5 volts. And V in just needs to be 2.5 volts greater than 5 volts. As long as we adhere to this and put in R1 and R2, this will work for us. And in fact, I made one of these the other day, and I will be posting a video on this little guy here, but this is exactly what this circuit is. There's just been a couple of things that I've added, but nevertheless, we have our LM317, and I created an adjustable voltage source by making this resistor adjustable. So instead of putting in a fixed value over here to get a fixed voltage, what I did was I stuck one of these potentiometers in here, and I'm using this potentiometer in order to give me an adjustable voltage. Okay, so there are some times when you actually do want to be able to change what that voltage is, and this was one of those times in this little device that I was creating for a little side project. I'm actually going to be using this on Friday for my workshop for testing out some multimeters. Okay, I actually wanted to create somewhat of a precision current standard or current reference for the sake of testing out my different multimeters. I wanted to maintain a fixed current, and I wanted to do that at different currents. So all I did was I put in one of these LM317s with an adjustable voltage, so I can change the voltage applied to this resistor over here, and then that gives me different currents flowing through the resistor, because the resistor stays at a fixed value of resistance while the voltage applied to it, I can adjust it up and down. So these LM317s, they have been around with us for quite a while, and they are fairly useful. I've used them in many different designs. Okay, so as long as we do this, we get 5 volts on the output. Is there any question about using this guy before I dive into a little bit of what's going on inside? Any questions?
I have a question. Go ahead.
Could I see that upper half for a second of the page? Thank you.
Kevin.
Yeah, did you just solve R2 that fast? Like, did you just know the value to it?
Oh,
Immediately?
I had it already solved.
Oh, okay, I see. Because you just solved that so fast, man. I was trying to figure it out, and you were already like 720.
Yeah, sorry
Okay.
about that. No,
makes
I
sense.
already had it solved. Trust me,
Makes
I can't
sense.
do math that fast. It'd be nice. I wish I could.
Yeah.
I think the best, when I was in college, the fastest person at mental math that I came across was a statistician. It was this older lady, and she was a statistician by trade, and she was teaching, I forget what math class I had her for, and she could do stuff like this before you could even like write down the equation. You just rattle off some numbers, she was already solving it. Any other questions? Everyone's comfortable with this whole idea of the dropout voltage. This is where I see most people mess this up. If I'm going to point out where I see failure in implementing these types of regulators, whether they're fixed or adjustable, I see students all the time violating this 7.5 if they're doing a 5 volt output, or you're doing a 3.3 volt output and your input is not 2.5 volts above that. So I see that most commonly. Okay, let's dive in a little bit into what's going on, because this to me feels a little bit of magic. Anybody else feel like there's just wizardry going on? Inside a voltage regulator. Now, this is applicable whether we're looking at an LM317 or an LM7805. They both have the same type of internal topology. Okay, so what's going on inside here? Let's label this as V in, let's label this as V out, and actually, let's make this a 7805. I'm gonna make this just our connection to ground. And let's go ahead and say that V out is equal to 5 volts over here. And since I already calculated this for our adjustable, we can use the same values here. Okay, so this is what's inside. And there's a couple of things here that probably don't make any sense. First off, we have this transistor. We haven't even gotten to transistors. And over here, we have this comparator. Okay, so I will not be testing on any of this as far as the internal workings, but nevertheless, I think it's worth it to take a look so we can kind of appreciate all the stuff that's given to us in this device. We also have our VREF, our reference voltage. This is a constant 1.25 volts. Regardless of what's happening out here, this device inside generates this 1.25 volts and uses it as a comparison to make with the voltage over here from this voltage divider. Okay, so let's talk about the parts that we have over here. We have our feedback resistors that are a voltage divider. We're just taking whatever the voltage is here, dividing it over here. This guy treated as an input. There's no current going in or out of this comparator. All it is looking at the voltage. And it's comparing whatever the voltage is at this point to VREF. And then we have this transistor. And what's the job of this transistor? Well, he's going to allow more or less current to flow through here depending on whatever happens over here. So you can kind of think of this as a water valve. Okay, so I'll use the water flow analogy for this. It's okay. Over here, more. Let me draw this in with red. And let's call this I. And I will call this IB. Okay, more IB equals more I. Less IB equals less I. Okay, so this is all that this is doing is acting like your sprinkler valve. We can, or your garden hose valve. So we are either going to allow a little bit of current through here, or we are going to allow a lot of current through here. Okay, depending on what we do on this wire. And the relationship, it's just proportional. More current going in equals more I going through it. Less current going into the device equals less current going through it. So all this is doing is allowing us to control the flow of current through our device and eventually through our load. Okay, now what allows more or less current to flow through our load is going to be the output from this comparator. In other words, we're performing a comparison. What are we going to compare? Well, on one side, we have this fixed 1.25 volts. And what are we going to compare to that 1.25 volts? The voltage going across our load. Okay, so when this is 5 volts, this is going to be 1.25 volts. That's what that equation was that we solved. Okay, so what happens over here? Now, the goal, of course, maintain a fixed V out. And we'll go ahead and say regardless of changes to RL. Now, RL can change on us. That's what it means to be a load. Loads don't stay fixed. Our laptop uses a different amount of current when it's sleeping versus when it's running. It uses a different amount of current when it's executing a multiply instruction versus executing an addition instruction. It uses a different amount of current if the LCD is on versus when it's not. So this load is constantly changing on us. And when it changes on us for a fixed value of current, that voltage across it will change, right? If I keep I through here constantly at 1 amp and our load fluctuates on us, the voltage across it will change. It has to. It's just Ohm's law, V equals IR. If I change R while keeping I constant, V will change. Well, that's what we're trying to avoid. We want to keep V at a constant value, specifically at 5 volts as we set up. So what is going on here is this voltage divider is actually taking a little bit of this voltage, and it's always getting divided by the ratio of these two resistances. So if this is 5 volts, we get 1.25 volts here. But if this is 5.1 volts or 5.2 volts, then this voltage goes up too. Well, what happens if 5 volts is actually goes up to, let's say, 5.2? Well, if 5 goes up to 5.2, then 1.25 changes. And this 1.25 goes up as well, and now the comparator sees that it is higher than 1.25. So it goes, oh noes, we have too high of a voltage, lower the current through here. And all of a sudden the floodgates start closing a little bit and allow less current in order to bring it back down to 5 volts. Everyone see how that works? So this voltage divider is, let's just say that this goes to like 1.3 volts. 1.3 volts is larger than 1.25 volts. The result of this comparison then lowers the amount of current going into our check valve over here. And so with lower current going in, we get less I going through it. And so now all of a sudden when you solve Ohm's law with less I going through it, it brings the voltage back down. Okay, and the same thing happens in the other direction. Let's say our load starts using it starts behaving like a larger resistance, and so the voltage starts going down. Let's say it goes to something like 4.8. Well, this voltage by the voltage divider then goes down as well. Say it goes to like 1.2 volts. You can solve for this. I haven't solved for this. I'm just speaking in generalities. But if this voltage that was supposed to be at 5 volts goes down to 4.8 volts, then this voltage over here, solve the voltage divider, V in V in times R2 divided by R1 plus R2, you get a lower voltage over here. And now the comparator looks at that and goes, oh, we need to increase voltage, increase current, put more current into here in order to drive this voltage back up. So this guy is constantly checking and adjusting, checking and adjusting. We call this feedback. So this is where the voltage regulator, where all of that work is done for us inside of this feedback loop over here. Okay, so you don't have to remember this. I'm not examining on any of this. We need to get another week before we get into this component, and we need to get another week into let's see, it'll probably be about a month before we get into this part. Okay, and then you can fully appreciate and understand what's going on inside of a voltage regulator. But for now, we just want to make it work. For now, we just want to use these guys. So we follow those rules of thumb, we place our filter caps, and we maintain our dropout voltage, and it will work. Okay. Any questions about this? Any questions like where does this magically regulated voltage come from in the first place? Like, how do I get a 1.25 volts always fixed regardless of what's happening out here? Did that thought cross anyone's mind?
Yeah, but I assumed you were just going to go over it when we go over comparators.
No, it's not a function of the comparator. This is actually coming from a separate circuit called a band gap generator. And if you want to know how this band gap generator creates a fixed 1.25 volts regardless of what's happening to V in, regardless of the temperature and the humidity and all of those outside factors, get a PhD in electrical engineering. I've looked up into this circuit. I know approximately how this circuit works. It actually does rely at the semiconductor level at those voltage drops across like a PN junction, and then it cancels out with two of them. It actually cancels out the effects of temperature and humidity. It's a very interesting circuit. Definitely well outside the scope of this class, but I wanted to highlight it because this just seems crazy. Now the thing is, a band gap generator can generate about 1.25 volts. It cannot generate 5 volts. So that's why we have to have these two feedback resistors. We need this voltage divider over here in order to reduce our 5 volts or whatever our desired V out is, in order to make the comparison to this band gap generator, because we can't make this band gap generator just generate any voltage we want. So that's where the necessity of this guy is, the feedback resistors. Now, I drew this for a fixed voltage regulator. However, look at our adjustable. All that they've done for us with the LM317 is they've moved those feedback resistors outside. So this is the point. This is the adjust pin right here. And we've brought out that adjust pin so we have the flexibility to add any feedback resistors we want. So that's the only difference between the LM317 and your 7800 series, is that they've allowed us the ability to add our own feedback resistors, where for a 7805, they just put it inside for us. Now, it does make it, when you have a fixed voltage regulator, it's a little easier to use because you don't have to add those external resistors. But yeah. And in fact, if I, let me go ahead and pull up a here we go. Here's a image of the band gap generator. If I close, okay, so when I just write 1.25 volts in here, it's worth acknowledging that it's actually this circuit over here that's being used. And what they're trying to do is they're using two transistors which do have PN junctions inside of it, and very similar to like our diode. And what they're trying to do is use two of them so that if temperature goes up, if temperature should go up for both of them. And so you take the difference between the two so you can cancel out those effects of temperature, and then you end up getting a voltage reference from that regardless of how your voltage changes up here. But like I said, this is a much more advanced circuit and takes quite a bit of work and effort to really understand how it works, and it's outside of the scope, but it's useful to at least acknowledge and know that you're not getting something for free. There's actually a circuit involved here. Okay, so you can always look that up if you're interested in how these work. You could make your own voltage regulator out of discrete parts by the end of class, and I think that's kind of a fun exercise. Okay, so let's go ahead and let's take a very quick, like 5-minute break so I can get set up for lab. And let's go ahead and let's I have some cool stuff for that power supply lab. So let's meet up in about 5 minutes. All right, thanks. Okay, let's go ahead and let's set up, let's see. So you guys should be done with the simulation with the voltage regulator with the entire power supply. And just to kind of remind ourselves what's going on here, we have 120 volts coming in. $120 volts coming in, and the first thing we do is we put it through a transformer, a step-down transformer, to reduce that AC voltage. And then we go into the full wave bridge rectifier, And then after our full wave bridge rectifier, we then set up this smoothing capacitor in order to flatten out that ripple, and I'll show those two differences. And we need to go ahead and add in those filter caps. So let's first start with what's in black for constructing this circuit. Okay, now as far as going mains into a transformer, here's a transformer. Now this is a little different than the transformer we used last time for taking the measurement, and it's a little different than what your simulation has. I have that other transformer over here. But this is no fun because the transformer is sealed up inside of this yellow box, and so I can't show you what the transformer inside of here looks like unless I take out a Dremel and cut this guy open. But a transformer in general looks like this guy, and I have it mounted to a block of wood. And we have a primary coil and we have a secondary coil, and they are right next to each other so that they share that magnetic field of the core material. Okay, now I do have a fuse for safety reasons going into here. So going into my transformer is 120 volts here, and if I shoved my fingers in there, well enough to get past this heat shrink tubing that I've put over here, then I could go ahead and shock myself. So for safety reasons, at least in the lab when everyone's in person working on this, we use these sealed transformers that put out an AC voltage that's been stepped down, and in fact this guy puts out 24 volts of AC. This is a bit lower. This is a 12 volt on the output. But nevertheless, at least so we can see what a transformer should look like inside of that sealed white package. Okay, and let me go ahead and adjust my camera over here. Oh, why did I just lose? How did I lose that video feed? Oh, I don't have it anymore. Something must have happened. There we are. Okay, we're back. So I'm gonna go ahead and move my move this camera so we can zoom in on the desk. Okay. So let's go ahead and let's first let's hook up that transformer, and we're going to hook up the transformer to a full wave rectifier. And let me go ahead and zoom in on the full wave bridge rectifier here. Okay, so hopefully the full wave bridge rectifier should be visible. Okay, so we have, I'm going to disconnect everything from here. So we have one diode where the cathode, this band, is meeting up with the cathode of the other one. This side is going to be our positive. And we have where the two diodes, where the anode meets up with each other, gives us our ground, or our negative side. Okay, so as far as the output, our outputs are here, and our AC inputs are here and here. Where the front of the diode meets the back end of the diode gives us one of our AC inputs, and the other AC input is where the front end of the diode meets the back end of the diode. Okay, so this is exactly that schematic that we've drawn before. This right here. Okay, and in fact, probably a little hard to see if I go ahead, if I orientate it this way. There, I think this makes a bit more sense. Okay, so our full wave bridge rectifier, we have the cathode going to the anode. Cathode goes to anode. And then we have cathode goes to cathode right here. Cathode goes to cathode. And we have cathode goes to anode down here. And we have anode to anode, which is right here. Okay, so we have our full wave bridge rectifier constructed on our breadboard using 1N4001s or similar. Okay, so I will leave that there. In fact, maybe over here would be good for now. Okay, now what we need to do, we need to take our transformer and attach it to those two inputs. So what I'm going to do is I'm going to take our transformer and I'm going to plug it into my power strip along the back over here. preferably without shorting anything. Okay, and now I have these two wires, which are the output from my transformer, and I need to connect those to my two AC inputs of my full wave bridge rectifier. And I'm going to do that with a couple of wires over here. So I'm going to clip one onto one side. You can kind of see that in the background over here. So the white wire is going to be one of my AC inputs, and I'm just going to clip it right over there. If you see on the zoomed in full wave bridge rectifier, I have it clipped in right there. Okay, and then I need the other side of my AC input. And now I have that clipped onto the transformer as well. So I have my two AC inputs, one right there and the other one over there. Now I need to bring out my positive, and I'm going to do that with a couple of little wires here. In fact, what I'm going to do is I'm going to use the negative rail along the bottom as my ground. So I'm going to take this and go into my ground rail right here. And then now I've established my ground, or my minus. Now let's take the positive and I'm going to change where my AC is clipped into so I can stay out of the way a little bit. And I'm just going to go in like that. Let me tilt the wire so you can see where the connections are being made on the breadboard. Perfect. Okay, now I am going to take, for this full wave bridge rectifier to work on a breadboard and for our waveform to actually look good on our oscilloscope, I do need to attach a little bit of a load resistance over here. So I'm going to attach a 1K, and then we'll change that once we add the regulator. This is where tweezers come in really handy. When you're working with breadboards, I find the wires can have some difficulty going in sometimes, especially on the cheaper breadboards we have access to these days. And a pair of tweezers really helps for plugging things in. Okay. So now what do we have? Well, we have the output of our full wave bridge rectifier going into this resistor, and the resistor is connected to the minus side output of our full wave bridge rectifier, and we have our two ACs going in. So all I need to do is apply power, and we should have our full wave bridge rectifier working. Now, to see this, I'm going to need to bring up the oscilloscope. So let's fire on the oscilloscope. I'm going to grab my channel probes over here. Okay, I have a channel 1 and a channel 2 probe. Okay, let's go ahead and let's take channel 1 and let's actually just probe the AC for now. Just the input to our full wave bridge rectifier. Make sure that we have exactly the AC that we intend to see. Okay, and let me bring up my O-scope interface over here. And I'm going to go ahead and let me kick on power going to the transformer here. So first time smoke test. Let's see. Hopefully nothing blows up. Okay, so now we should see some AC on our oscilloscope. Let me bring that up, and sure enough, we do. Okay, now it's not moving on us anymore. And let's see what the voltage on the input. Okay, so right here I moved that vertical cursor over to the highest point of my waveform, at least what looks like the highest point of the waveform, and looks like we're getting about 36.0. In fact, let me bring up the horizontal so that it doesn't move around on us as much. About 36.8 volts peak on the input. Okay. That might be a little different than what we measured last time. What did you guys get for your output from the transformer in the simulation portion? Right, we did, as we were working on lab 2, the power supply modeling and construction. We calculated the inductance values to create a transformer inside of LT Spice. What did you guys get for that output? How many volts coming from a coming from the mains after the and then going through the transformer and then stepping that voltage down? It was what, 35, 36, 37? Help me out here.
I got
I'm
37.
not the one doing the lab. Huh?
I got 37.
37. Okay, perfect. Okay, cool. So right now I'm getting 37.2, a little differently. Okay. So now what I would like to show you is the output from the full wave bridge rectifier and the input to the full wave bridge rectifier, right? We would like to see, if you follow my cursor over here, you should see it. Okay, you see my cursor on the waveform, right? We should see a positive pulse when our AC input to the full wave bridge rectifier goes high. We should see the blue line eventually, when I hook it up, go high. And then when our AC goes down into the negative range, we should see another positive pulse here, and then another positive pulse. So we should be rectifying on both the positive and the negative alternation. Now, there is a practical problem with doing this with an oscilloscope. This falls under the how to not blow up your oscilloscope lecture series. Let me take you to the whiteboard to show you the problem with doing this. I can't just stick my second probe on the output. Okay, here's the problem with probing both the input and the output of your rectifier. And I think this is a very valuable thing to learn about an oscilloscope. Okay, if I take my channel 1 probe and attach the ground. I have to attach this ground reference at one of these points of my AC. And I have to do that with my other probe as well. So channel 1 I've drawn in blue, channel 2 I will do in red. Now, in fact, let Let me make the ground clip of each probe. Let me make it in black. And that way, I can show what's going on here. Okay, if I hook up one probe on the input and I hook up another probe on the output, I have to attach those ground clips somewhere. And if I attach them where they're supposed to go, notice inside of my oscilloscope, those two black alligator clips, these things, are actually connected to each other. And so what's going to happen is I'm actually going to short out this diode over here, and the diode's going to break down. Actually, one of the other diodes is going to break down on me. I'll lose two diodes when this happens by shorting out one of these diodes. I'll create a situation where a lot of current flows through two of these diodes, and they will break out, and I will end up shorting out the two ground clips from my oscilloscope. And so I actually can't take this measurement. What I can do is I can hook up one probe and then switch to the other side and then show you that. So let me go ahead and do that. I'll do that first. So this is our input. And now let's go ahead and look at the output. Cool. I think my resistor is too small of a value. It's getting really hot. Okay, so now you can see the output from the full wave bridge rectifier. You should have an AC that goes up here and then comes down and then goes back up and then comes down and goes back up, etc. Right? So that's really cool. And let's go ahead and take a measurement here. $35.6. Okay. There's your peak voltage of the pulsating DC from the output of the full wave bridge rectifier, 35.6 volts. So remember that value, put it in your lab write-up, whatever you're going to do. Okay, now I do have a way that I can actually probe both the input and the output at the same time. Okay, I actually made a little differential amplifier last night just for this purpose. So I have one probe looking at the output right now. That was the pulsating DC. Now let's go ahead and let's probe that input. Using my little homemade differential probe amplifier circuit. And then we can see the input and the output at the same time. I'm going to need, let's see. Let me apply power over here. And let me make sure I plug this all in correctly. Okay, my positive, wait. That is minus 15 going to black, positive 15 goes down here. So don't worry about this circuit that I have on the green breadboard. And my output should go here. Okay, so now my red and gray probes here are technically my oscilloscope. They're just going through this little circuit down here, but my oscilloscope should show it now, provided okay. Let's see if we can see both at the same time. Okay, promising. There's some aliasing on my channel 2. Let me fix that by probing, or by actually changing my trigger to channel 2. Okay, cool. And now, let's see, their volts per division is off. Okay, now they're both set up at the same 20 volts per division. Okay, that looks awesome. That looks beautiful. Okay, so check this out. That circuit that I just hooked up is probing the input to the full wave bridge rectifier, and there's our AC coming out from the transformer into the full wave bridge rectifier. And then our rectified voltage is the yellow line right here, and you can see those two voltage drops. Right? So the measurement that we got was 35.6, where our input was 37, right? So 37 volts minus 35.6 gives us a voltage drop of really 1.4 volts. And that 1.4 volt voltage drop comes from the two voltage drops of our diode. Remember, whenever we're conducting, we have two voltage drops of the diode in our rectifier. So 2 times 0.7 volts gives us 1.4 volts. That's pretty good. That's pretty spot on. Now, I think a little bit of that is just luck with where I put the lines. Usually it's a little less precise than that, but it looks like we got pretty spot on, at least as far as what we would think of on the whiteboard. Okay, so where are we at now? What do we need to do? We need a smoothing capacitor, and we need to filter out those that pulsating DC ripple, right? Okay, so let's go ahead and let's add a 22 microfarad cap in order to smooth out that pulsating DC. So I'm going to minimize the oscilloscope, and let's find ourselves a 22,000 microfarad cap. Okay, this is 1,000. I got 4,700. I got more. Okay, let's see, what's this? 125, here we go. 2200. Okay, I think I kept saying 22,000. I meant 2200. That's what our lab document calls for. Yes, at a 2200 microfarad cap. Okay.
Professor,
Yeah.
I think last lab we were using, we were at peak to peak voltage of 75, so 37.5 at peak voltage, not
Oh,
37.
37.5?
Yeah.
Someone else said it was 37 earlier, so I went off of that.
Yeah, I'm just going off of what I think what we had the previous lab session.
Oh, okay. Yeah, just put down
Yeah.
down 37.5, put down 37. I think it's not that big of a deal in the grand scheme of things.
All right.
Okay. So, we need to go ahead and hook up this cap, but we are also going to need a 100 ohm load resistance. Okay. So, I'm going to need a big resistor that can take a lot of power. Fortunately, I got these giant things over here. These are flame-proof resistors that will not catch fire, but they will get really hot. $25, $10. Let's see. I got 25 and 10. 20. 20, 20. $5.1. Here, I have a little smaller 100. Let's see. If I put those two together, I get 40, 60, 70, 80, 90. Oh. If I put all of these in series, I will get 100 ohms. All right, let's put all these in series. Oh, okay. Shoot, a couple of them just broke. Okay, I have another, let's see, a 40, a 40, and a 20 should do it. Okay, and let's kind of get an idea for how much power is going to be dissipated by this circuit. Now, our pulsating DC does go to, let's see, 35.6 volts, right? Okay, so 35.6 volts peak. Okay. Now, if we want to get our Ohm's law and power relation back, keep in mind it is a, well, because it's pulsating DC, we're going to add that cap. So we can actually just use this voltage as is to figure out the current and then apply P equals IV with our resistance of 100 ohms, and we should figure out what the current is. What the power is. So let's do 35.6 volts divided by 100 ohms gives us the current. 35.6 divided by 100 ohms gives us, that's a lot of current. And now take that and multiply that by 35.6. 12 watts. Are we really doing 12 watts into this? Looks like it. Okay. So this is actually going to be quite a bit of power. And I'm going to grab some more test leads. Okay, kind of tricky trying to keep everything on camera. Let's put that cap in there first. Okay. So I have my cap in there. And now if we look at the voltage across, now keep in mind, we don't have a load resistor yet. So we're not going to see any ripple. We're just going to see a flat line because there's no way to discharge that cap right now. So if I go back to, yeah, check out our channel 1 that's looking at the output. It's just a flat line. We don't have any ripple because there's no way to discharge that cap. So it's just getting charged up and it's staying at that constant voltage level. So our pulsating DC just got replaced by a perfect flat line. In fact, if I go, well, you'll see this once I add the load resistance in here. And what's that voltage? Yeah, the voltage across the cap is DC at 35.6. That's kind of exactly what we expect it to be. So now let's go ahead and let's add. I'm going to use this red wire for one side of the resistor. Let's attach this over there, and then I'll use a green wire for the other side of the resistor. And maybe at this point, okay, there you can see my load resistor is here with a red wire jumping over to the cap and then the green wire over here. And cool. Okay. I can't keep it hooked up for too long. These are going to get really warm after a while. Okay, let's go back to the oscilloscope and let's see what happened. Don't pay attention to the blue. The blue that's going on, it just turned from a sine wave into a trapezoid. That has to do with my improvised differential probe that I made just so that we could look at the input. In fact, I'm going to disconnect that for now. Okay, take a look at the yellow. It looks like it's not so flat anymore. It looks like there's some ripple in there. However, I'm too zoomed out. This is at 35.6 volts. So what I'm going to do is I'm going to remove the DC offset. So from 0 volts to 3.5 to 35.6 volts, this is the DC offset over here. My scope has the ability, this is what's known as coupling. If you change the coupling from DC over to AC, wait, why did it not get centered? Do I have to... Why are we still up there at 35.6? Oh, because that's channel 2. I need to do it for channel 1. Channel 1, change coupling. There we go. Okay, now that brings it to center. I'm going to turn channel 2 off so that we're only looking at channel 1. And you can kind of see the ripple there now. And if I change the volts per division so that we zoom in... Hey, okay. And let me set up the trigger. Very cool. There's our ripple, okay? Oh yeah, resistors are getting very toasty. Okay, so let's go ahead, let's take our measurement of this ripple voltage now. It looks like we're getting 400, delta 838 millivolts of ripple. Maybe a little less than that. Ballpark, 800 millivolts of ripple. Okay, and if I remove my cap, we should get no ripple. Sorry, if I remove the load, I get no ripple. Okay, but with the load in place, you can see that now I'm discharging that stored energy in the cap when our pulsating DC is going down. Okay? So 800 millivolts of ripple. And my resistors are very hot. Okay, so that should get us through the lab with the exception of the regulator. So we'll add the regulator to this next time. Okay? Okay, so that's everything.